Now that we've looked at our Lewis structures and we have determined our molecular geometry based on our VSEPR formulas, we are going to look at our overall bond polarity and then our molecular polarity. Now the first part of it's actually pretty simple. All we need to do is look up these numbers on the back of our periodic table for the electronegativity of each atom that's involved within our bond. So we have chlorine is 3.16, we have beryllium is 1.57. We don't multiply the chlorine by 2 because each bond only actually has one chlorine. So we just take 3.16 minus 1.57, that gives us 1.59. 1.59 falls within our range of a polar bond, and on the polar bond we draw our dipoles. The dipoles always point toward the higher electronegativity. So for this atom, that's the chlorine, and again over on this bond, also pointing toward the chlorine. Once we have our bond polarity determined, we look at our dipoles, we consider the shape of the actual molecule, and then we determine whether or not those dipoles cancel. For beryllium chloride, the shape of the molecule is actually linear. It's AB2, there's no E's, which means that our dipoles are actually directly across from each other. And since the dipoles are directly across from each other and they're opposing each other, they're pulling against, they do cancel. And since they cancel, there is no overall dipole moment, which means the molecule is nonpolar. For something like water, it's a little bit different. Even though when we subtract the hydrogen and the oxygen's electronegativity, the bond is polar, so we would draw our dipole originally toward the oxygen, like that. When we consider our shape, because we have these E's now, AB2E2, that's a bent molecule. And because those dipoles aren't actually both pulling toward each other anymore, they don't really oppose each other. They're not directly across from each other, and they're not symmetrically or evenly distributed. So really think about it as these electrons are getting shifted up and toward the right. These are getting shifted up and toward the left, but there's nothing pushing back down. So all of the electrons would actually wind up toward the top of this molecule. And oftentimes in your sketches, instead of showing the individual dipoles, you'll even see these little symbols that look kind of like this to show which end of the molecule is a little negative and which end of the molecule is a little positive. The direction that the dipoles don't cancel is the side that gets the little bit negative. So right now you might be thinking, okay, this is pretty simple. If it doesn't have dots, then they can cancel. If it does have dots, they don't cancel. And for a lot of the examples, you're right. But that's not saying that every single example is like that. So here in hydrocyanic acid, we have two different polar bonds. Notice I took the electronegativity of the carbon and the hydrogen, that would be this bond, subtracted those, and then I took carbon and nitrogen, that's this bond, and subtracted those. Nowhere do I subtract nitrogen and hydrogen because they're not bonded together, and I don't subtract all three of them at once. I just look at the two elements that are within each bond. So the carbon-hydrogen has a dipole pointing toward carbon. The carbon-nitrogen has a dipole pointing toward the nitrogen. The shape of the molecule would be AB2, so that's linear. But this time, our first dipole points toward the central atom and the second points away from the central atom. Since both of them are pointing toward the right, they're not going to cancel. And if they don't cancel, this molecule is overall polar. And again, instead of drawing the individual dipole arrows, we might just draw the dipole moment. This side of the molecule, where the arrows are all pointing, would be a little bit negative. This side of the molecule would wind up being a little bit positive. The fourth example I have here is ozone, that's O3-, which when we take 3.44 for the first oxygen minus 3.44 for the second oxygen, obviously we're going to get a 0 for our electronegativity difference. 0 electronegativity difference is below 0.4, which means the bonds are nonpolar, which means the molecule is automatically nonpolar, even though this one would also actually wind up being bent since it has the pair of dots on the center, which I totally didn't forget. The bent molecule doesn't have dipoles drawn, and since it doesn't have dipoles drawn, it's not going to be a polar molecule. So quick review before we move on. Nonpolar molecule because the polar bonds cancel. Polar molecule because the polar bonds do not cancel. Polar molecule because the polar bonds do not cancel. And nonpolar molecule because there were no polar bonds. Overall, those are the things that we have to consider. Now, as we go through this, we have a lot of shapes, and so it might be better if we kind of think in terms of categories. Shapes where dipoles might cancel versus shapes where they wouldn't cancel. So if we think about our very first shape, diatomic linear, there's only 2 lines there. If you have an atom that is a diatomic linear atom, it only has 1 dipole, and since there's only 1 dipole, there's nothing to cancel that dipole out. That means that if this molecule has dipole, it will be polar. Similarly, the bent shape, regardless of whether it has 1 pair of dots or 2, the trigonal pyramidal shape, the T-shape, the square pyramidal shape, the seesaw shape, all of these shapes are going to be polar if there are polar bonds. So if there are polar bonds, there are dipoles. Those dipoles cannot cancel because of the geometry of the molecule, because the bond angles are not all identical. These molecules, if they have polar bonds, will be a polar molecule. The other shapes, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar, which is the only one of the shapes that has dots with it. These are known as symmetrical shapes. If they have dipoles and the dipoles oppose each other, these are the shapes where all of the angles are equal and they can cancel. So if you have dipoles on all of the bonds and the dipoles oppose each other, either both in or both out, then these are the shapes that will be nonpolar overall.